Welcome to Master Mathematics in Minutes. Today's topic is the chain rule of differentiation, and we'll cover a couple examples on how to differentiate polynomial functions. And we'll conclude the topic with a summary. And finally, be kind and subscribe for more videos. So, what is a chain rule? The chain rule states that dy dx can be written as dy du multiplied by du dx. So u is the common variable here that connects y and x, and that's how we've combined them with the chain rule. And for a given composite function of the form yx, which is equals to the function f of g of x, we have dy dx, which is equals to the y prime of x, and that is equals to f prime evaluated at g of x multiplied by g prime of x. So the first step is to differentiate the first function, and that gives us f prime. And the second step is to copy the second function, gx. And the third step is to differentiate the second function, and that gives us g prime of x. On the next slide, we'll have a look at how the first equation is related to the second. So, given the composite function yx is equals to f of g of x, we're able to substitute u is equals to g of x. So what we look to do is to replace that g of x with the letter u. And then we'll differentiate. So we have yx, which is that yx, and that is equals to f, which is that f. And we'll replace gx by u. And so that becomes u. And we've copied that u equals to gx here. U is equals to gx. And we will then differentiate the functions y as well as the function u. So we have dy du is equals to f prime of u, and we have du dx is equals to g prime of x. And so we're able to apply the chain rule. So the chain rule states that dy dx is equals to dy du multiplied by du dx. So that was the first line in the previous slide. So we'll substitute this term and this term with what we've calculated here. So with dy du, which is that term, and that is f prime of u, copy that f prime of u here, and with du dx, which is that du dx, and that is equals to g prime of x, and we'll copy that down here, g prime of x. And we'll substitute u, which is that u, as gx again, and with f prime evaluated at gx times g prime of x. We'll have a look at a couple examples now, which will greatly assist in the visualization of how the rule is being applied. In the first example, we're asked to differentiate the function yx, which is equals to open brackets x squared plus 1 close brackets raised to the power of 3. And notice that this is a composite function. We have the internal function as x squared plus 1, and the external function as a function raised to the power of 3. And so we're able to apply the chain rule. So we've stated the chain rule results here. It was identical to what we saw earlier. And the first step is to define the function f as well as the function g. So the function f, which is that function f here, we'll set that to be the external function, which is the function that raises to the power of 3. And we'll call that x to the power of 3. And gx, which is that gx here, we'll set that to be the internal function, which is x squared plus 1. So write x squared plus 1. So now that we've defined the functions f and g, we're able to differentiate these functions. So f prime of x is equals to, we'll drop the power to the front, that becomes 3, times x to the power of 3 minus 1, because we're differentiating here. And that simplifies to 3x squared. And g prime of x, dropping the power to the front, that gives us 2, and multiply by x to the power of 2 minus 1, again reducing the power because we're differentiating here. And differentiating a constant gives us 0, and that simplifies to 2x. So we've calculated the terms that we need, which we can then substitute to dy dx and apply the chain rule. So we've stated the results of the chain rule here. So this line is identical to that previous line. And we will then do the substitution now. So starting with the function f prime, that equals to that function f prime, and that is 3x squared. So you're multiplying x by 3 and you're squaring x. So we'll multiply that by 3 and we will put a square there. And because this is evaluated at g of x, we're bringing g of x as x squared plus 1. And that gives us x squared plus 1 in here. And g prime of x is at g prime of x, which is 2x, which we'll copy as 2x. So all we've done so far is substituted the respective terms to apply the chain rule. And 3 multiplied by 2x gives us 6x. And we'll copy the squared, x squared plus 1, holding squared. And with 6x again, and we'll expand the squared. And so x squared squared is x to the power 4. X squared times 1 times 2 gives us 2x squared, and 1 squared gives us 1. And expanding the brackets, we have 6 times x to the power 5, and 12 times x to the power 3, and 6x. So, given a composite function yx, we're able to find the derivative of the function dy dx by applying the chain rule, and that gives us the derivative. In the second example, we're asked to differentiate the function yx is equals to, open brackets, x to the power 5, plus 5, close brackets, everything raised to the power of 10. Notice that this is a composite function, with the internal function as x to the power 5 plus 5, and the external function raises everything to the power of 10. And so we're able to apply the chain rule. So take the chain rule results again. This is identical to what we saw earlier. And the first step is to define the function f and the function g. So we have fx, which is that f, and we'll define that to be the external function raised to the power of 10, and so with x to the power of 10. And with gx, which is that gx, and we'll define that to be the internal function, and with x to the power 5 plus 5. So now that we have the functions f and g, we're able to differentiate them. So starting with f prime of x, we have equals to, we'll drop the power to the front, that becomes 10, times x to the power of 10 minus 1. Remember, because we're differentiating, we will reduce the power by 1. And that simplifies to 10 times x to the power of 9. And differentiating the function g, that is equals to, again, we'll drop the power to the front, that becomes 5, times x to the power of 5 minus 1, because we're differentiating, and differentiating a constant 5 gives us 0. And that simplifies to 5 times x to the power of 4. And now that we have the terms that we need, we're able to substitute that back into the chain rule to calculate dy dx. So with dy dx restated again, so these two lines are identical, the next step is to substitute the terms. So starting with f prime, and that is equal to 10 times x to the power of 9. So with the 10, copy down here 10, and we have to the power of 9 to the power of 9 here. And because this is evaluated at the function gx, we'll copy the function gx in here. And that is equals to x to the 5, plus 5, and plus 5. And then we have multiplied by g prime of x, and that is equals to 5 times x to the power of 4, which is this term here. And so simplifying that, we have 50 times x to the power of 4, open brackets, x to the power of 5, plus 5, close brackets, raised to the power of 9. And so, given a composite function, we're able to calculate dy dx using the chain rule. To summarize, the chain rule states that dy dx is equals to dy du multiplied by du dx. Or, if we have a composite function yx is equals f of g of x, we have dy dx is equals to y prime of x, and that is equals to f prime, evaluated at gx, multiplied by g prime of x. Thank you very much for watching. This is Master Mathematics in Minutes.